All right, welcome back, everyone. Today, we're going to be diving into Chapter 7. Chapter 7 of the Digital Investigator's Handbook, and this is all going to be focusing on Linux and Mac forensics. Now, for the exam and in your careers, you can't afford to have tunnel vision just on Windows. Linux runs the majority of pretty much the world's web servers, IoT devices, and even cloud infrastructure. So, meanwhile, Mac OS is highly prevalent among developers and C suite executives. So, we're going to need to know a little bit about all of it. So, today we're going to be mastering the ext4 file system and the Apple APFS file systems because these are going to be critical artifacts that we need to understand with these Unix based operating systems. So, we're going to have three main objectives for this module. First, for Linux operating systems, you must master the ext4 file system. Deeply understand inode structures and map out the boot process, specifically the modern system deinitialization. That's what we'll use today. Secondly, we're going to be looking at the Mac systems. We're going to break down Apple file systems, the concept of containers, and specifically those high-value artifacts like the FS events or the unified logs. And then finally, for both systems, we're going to emphasize a little bit on those command line skills of yours. Unlike Windows, which is heavily GUI-driven forensics tools, we have to understand that the Unix system often requires a live forensics triage using bash or even the ZSH commands. So let's start with Linux. Now, the absolute core of everything you must grasp within Linux is everything is a file. Because of the virtual file system architecture, the operating system treats hardware, processes, and directories the same way as it treats a simple text file. Hardware devices are represented as files, and they're normally going to be found in the /dev directory, such as dev SDA. That's going to be your first hard drive. Now, running processes are going to be found in the proc directory, otherwise known as a /proc directory. As a forensic tip, this is going to simplify our jobs. We can create a bit-by-bit image of the entire hard drive simply by reading the file using like dd command. So the dd command would be ddif equals, where's that at? So maybe it's dev, the SDA, the first hard drive, and maybe our OF, our output file, will be image.dd. Now, for the exam, be familiar with dd, ddfldd, and dc3dd. Ooh, I can talk. dc3dd. Now, these are all forensics variations of DDs that will also help create hashes on the fly. For those who actually did the live environment test for this chapter already, realize we only dealt with DD, but I did not have you do DCFLDD or DC3DD because, well, we were going to mostly use the FTK imager for this class. But just be aware that those tools also can do hashes on the fly. Boop. Here we go. Trying not to skip too many slides here. So the default file system for Linux distributions is going to be the ext4. And you need to know its anatomy, okay? The disk is going to be divided into block groups. The very first block is the boot block, okay? Now this is going to have the bootstrap code needed to start the operating system. This is where the old grub files used to live. Okay, we used to like say where is the boot block for this loader to go, and it would point here. Now next is going to be the super block. Now this is the most critical metadata structure on the drive. It's going to have the block size, the number of blocks, and the numbers of used and free inodes. We'll talk about inodes here in a minute. Now, if the super block is corrupted, the OS can't read the disk at all, okay? Now, be aware the ext4, though, always is going to create a backup of its super block at specific boundaries that you can use to recover the drive. So just because someone destroyed the first super block doesn't mean there might not be a backup somewhere else on the drive itself. Now, following the superblock is the inode table. The inode table is the database of all the files within the system. Think of it like the file allocation tables when we're dealing with Windows. So let's look more into that inode itself. So the inode, or the inode index, it's a foundational concept for the exam. The inode stores all the metadata about a file except its name. It does not have the name of the file. So it's going to store things like the file size, the owner ID, normally the UID, the group ID, the GID, and the permissions, rewrite or execute, and direct and indirect pointers to the actual data blocks on the disk. Where is it physically located on the disk? It's also going to store the MAC times, remember, modified, modification, access, and change. And normally change refers to the inode metadata itself and not the file creation time. So it's a little bit different. It's only going to show you the inode metadata and not the file itself. Now, critically, the file name is not stored in the inode. File names are stored in the directory file, which simply maps human readable names to an inode number. Forensically, when a file is deleted from Linux, the inode is marked as free, and the directory link is broken, but the actual data still is going to be in the data block until it's overridden. So you can view the inode directly by using the stat command. Okay, so if you use a stat, you can see the inode data itself. And what we do with the stat command today is we'll use stat with the file name itself, and it will give you all the information, including the inode information, all the metadata, everything that's included. All right. Now, understanding the boot process is critical because malware, especially rootkits, will attempt to hijack it for persistence. So the Linux process is as follows. It's going to start with the BIOS, or the UFI performing its post, right? Power on self-test. Once the BIOS is ready, or UFI, it will then hand it over to either the MBR or the GPT. Remember, BIOS normally goes to the MBR and UFI is normally GPT, which will load the bootloader. In modern Linux, it's almost always going to be the grub, right? The Grand Unified Bootloader. That's the bootloader that it's going to look for. Now, grub's job is to load the actual Linux kernel named VM Linux with a Z into RAM. The kernel mounts the file system and executes the first user space program known as init. And remember, the very first ID for everything is going to be PID of 1. The init process, normally systemd, is going to have PID of 1, and it's going to start all other services. So if we look at a service and it has a PID of 1, and its parent ID is PID of 1, we know that systemd started it. Now, you'll still be tested on the old versus new initialization systems, and so we need to know the different systems. Now, systemd is the new modern standard. It speeds up the boot time by using parallel startup of services. Instead of numbered run levels, systemd uses targets like graphical target or multi-user target, and you can manage it using the systemctl command. Attackers love creating systemd services called .service to ensure that their backdoors survive a reboot. Now, the sysv init is the older system. It's the legacy system. And this is what we used to use, which was a sequential startup method based on run levels of 0 through 6. Think of it like the reading levels of Windows. It's basically what we used to do. The system startup scripts are normally located in etc init.d or rc.d, and if you're investigating in older servers, you must check these directories for rogue scripts, because this is where the persistence, as I said, will happen, where there might be a script in here that will launch malware or a persistence mechanism for an unauthorized piece of software, okay? And unlike Windows, who uses .evtx files, right? The event x files. Windows logs most things in just plain text, okay? And they're normally going to be found in the var log file. Now, you must memorize some of these files, like syslog or messages, generally is going to be system activity. The auth log or secure, depending if it's Red Hat, is going to be most critical log. It's our secure log, okay? It's our security log. It records all authentication attempts, and we can even be finding things like SSH brute force attacks or anything like that, because we can run grep against this file to look for like failed password storms, okay? We have the kern file, and this is where all the kernel messages are normally located, which is excellent for finding poorly generated things like crashes or rootkit errors. And this is where you'll find that. And then you got dmessage. Dmessage is all your boot logs and your hardware detection messages. So if you're wondering if a USB was plugged into a Linux machine, normally you can find that information in the dmessage directory. Other artifacts to be looked for is going to be, for one, is going to be in the etc directory. The etc password directory is going to list all the user accounts. A major red flag is finding a newly user account that has a UID of 0, because UID of 0 is normally a root, that's for root privileges. And so basically they secretly granted themselves root or administrative privileges by using a UID of 0 instead of what a traditional UID they would be assigned. So most users are assigned a UID of 1,000 or greater during normal creation, but 0 is reserved for root or administrative access only. Now the etc shadow file, on the other hand, is where the actual password hashes are. A single X in the password file means the OS should look in the shadow file for the hash. Now, the reason why we put it in 2 different files is it ensures that no service accounts like FTP or Apache have valid hashes, so they should not be allowed to log in interactively. And then finally, we'll find things like the etc cron tab, where we will manage the scheduled tasks. So, like Task Scheduler in Windows, cron tab is what we use in Linux. It is incredibly common to find malware to have persistence here. Like they may have a cron tab scheduled to run like crypto miner every hour or something in that nature. Okay. To track what a user is specifically doing, we do have some extra files that we can check. The first one's going to be our bash history file. It's going to contain a whole bunch of plain text logs for the commands for each user. Attackers frequently forget to wipe this. You should look for commands like wget or curl, like for downloading malware, or like rm-rf for destroying evidence, or even any base64 decoding commands. Note, Sophisticator attacks were going to run like unset hist file or kill-9 to prevent their current session from writing to this file. Also look for hidden files that start with a dot. So anything that starts with a dot is a hidden file. Like in the .ssh directory is critical. Attackers will also often drop their own SSH key into this file, granting themselves permanent passwordless backdoor access to this compromised account. Basically persistence for those who took Pentest Plus. Now, when responding to a live Linux system, the proc system is your greatest asset. And the reason for that is it's a virtual file system that resides entirely in RAM. It's going to provide you a real-time window into the kernel and have a whole bunch of cool information that we can analyze at a later time. So proc mem info will have all memory usage statistics. More importantly, every process running gets a folder named after its PID number. So you'll be able to find that, and you'll find it in proc PID and then maybe the command line. Okay. And so this is going to show the exact command line arguments used to launch the malware itself. Proc PID exe is a symbolic link back to the actual executable on the file. It's a massive So a massive tip here is if an attacker executes malware and then deletes the file from the disk to hide it, the executable is probably still mapped in memory. You can specifically recover the deleted malware directly from RAM by just copying the proc PID exe to your forensics drive. Now you still have the file that you just pulled right out of memory back as to a physical file again. So even if they try to delete it, if you can pull the exe from the proc PID, you have a copy of the executable still. Okay. All right, let's move on a little bit from Linux to Mac. All right, Mac forensics. Mac OS is essentially BSD with a shiny coat. Okay, because it's built on Darwin, a Unix derivative, many of your Linux commands like ls, dd, and grep will just work natively on a Mac terminal. However, app adds complex proprietary layers. The modern file system is called APFS. The hardware is secured by a T2 security chip, kind of like our TMP, our hardware chips that we do in Windows, but it's a T2 security chip or a modern M series Apple Silicon chip. Now, what this does is it provides hardware level encryption natively. Furthermore, Apple uses what we like to call SIP, System Integrity Protection, known as rootless .zip. So this is going to restrict the root user from modifying core system directories, which prevents malware from installing traditional root scripts, which often is going to complicate our forensics lives even more. Because for one, remember, we've got full level complex proprietary encryption. So in order to pull the drive, sometimes we can't pull the drive from the chip because that's what's going to provide the keys for decryption on a Mac system. So for the exam, we must know a little bit about the Mac file systems. HFS is their legacy. It's Mac OS Extended, okay? It's a legacy system used before Mac OS of the High Sierra model. That's the latest one, which was 10.13. It utilized journaling to keep a log of changes to prevent system corruption during sudden power outages. So if the power outage did happen, it could go look at its journal, see where it was, and pick up where it left off. Now, the Apple file system, on the other hand, is optimized for flash and SSD storage. And this is the reason why it was originally developed was for flash and SSD storage, because the old system, HFS, just killed SSD drives and flash because of this journaling system that just wrote the same sectors over and over and over. And so it introduced several new concepts. Instead of a rigid partition, it uses containers that can hold multiple volumes. Free space is shared dynamically across all volumes within a container. So it also uses things that's copy on write. If a user duplicates a 10 gig movie, APFS doesn't actually copy the data, it just simply creates a pointer. It takes 0 extra space until one of those files is actually modified. So it uses a lot of hashing systems to make sure that, hey, if I have 10 copies on my hard drive, I'm only going to store it one time. And so that did help when it came to video processing, because a lot of people like to have their resource files in the same directory, even if they used it 20 times over. And so it saved a lot of storage within their file system. Now, boop. APFS architecture, as I said, this is what we're going to be running now. Now, the container is the outer wrapper. Think of it like the partition. Inside the Mac OS, it splits the drive into 2 main volumes. The system volume is 100% read-only. It contains the core Mac OS system files starting in Big Sur, and the volume is encrypted or cryptographically signed with an SSV, a signed system volume. There we go. Meaning if any bit in the system is altered, Mac will refuse to boot. So this is just a very secure way of making sure the operating system doesn't get modified without it being intentional, without a system update. The other volume is our data volume. This is our read-write volume, and this is normally where all the users are going to live. This is where the third-party applications are and all the configurations. So this makes it, the split is invisible to the user. They can't see the differences because APFS uses firm links, which is bidirectional links that simply just merges both of the system and the data volume. So they look like a unified C drive in Finder. So if you look in Finder, it just looks like C, but it really is 2 partitions that are merged into one. Now the APFS snapshots, on the other hand, this is the new forensics this is something that's good for forensics, okay? This is our forensic advantage, is snapshots, because APFS can create an instant read-only snapshot of its entire file system state. This is deeply integrated into Time Machine and OS updates. If a malicious insider deletes evidence or empties their trash, that might still exist in a perfectly preserved in a local APFS snapshot from a few hours prior. Examiners normally you will mount these snapshots to view the systems exactly like they did in the past, entirely bypassing the user's attempt to do data destructions. So very, very, very useful. It's kind of like the VSS in Windows. It's just the Apple equivalent. Now, here's the Mac boot process. It's going to be the most secure operating systems because it's mostly driven by hardware. Now, it's going to start its boot ROM, which is the hardware root trust burned into the silicon chip, okay? The boot ROM is built into the chip. It cannot be changed. It passes into iBoot, which is its bootloader, which is verified through cryptography to ensure that the signature of the operating system kernel does match. If it does match, it will then boot the XNU kernel. And finally, instead of systemd, it's called launchd. Will launch into launchd, which is similar to the systemd in Linux. Launchd will have a PID of 1 and manages all other services in daemon. Now, because Secure Boot is enforced by the T2 or the in-chip series chips, a forensics investigator cannot simply just plug into a Kali Live USB and boot the Mac. You have to physically, you are physically blocked from booting unsigned OSs unless you boot into recovery mode and deliberately lower the system security posture, which can be done, but it is much more difficult because they're normally protected by passkeys that you may have to obtain from the user. So how do you actually get the data? Well, because of the hardware locks, acquiring an image of a Mac requires specific methods. Target disk mode is a legacy method by Intel Macs. By holding T on the boot, you can turn the Mac into a giant dumb external hard drive. That's the easiest way to do it. So you can connect your forensic station through a Thunderbolt connection through a write blocker, and now you can do the same thing. Now, Mac sharing mode is the modern equivalent, okay? And so it's a specialized recovery mode that allows you to share the internal SSD over an SMB network connection for images. Live imaging requires booting from a trusted USB like Macquisition or Recon TR, so you may need special tools to make this work. But as mentioned, you have to authenticate and lower the secure boot method to allow USB to load in the first place. Macs are a pain in the butt. All right. Once you have the image, what can you look for? Well, first are going to be property lists. Property lists are plist files that you'll find. Think of it like the registry for a Mac OS. They store preferences and configuration files for both the operating system and individual apps. They are formatted in either plain XML or a compressed binary format. To read a binary plist via command line, you need to use a tool, but it is built in, which is nice because you can use plutil-p and the plist file that you're looking for, and it will actually read it. So keylist files, info.plist, found inside of application bundles, can tell you things like application versions and requested permissions. Like com.apple.loginwindow.plist. Well, that dictates that which applications are auto-launched on startup. It is also definitely a place where people like to hide the malware. That's the best. That's the place that malware is normally hidden within a Mac. One of the most powerful artifacts of Mac is the FS event. Okay, and we often call it the flight recorder. It's located in a hidden file called .fsevents.d/. I can speak, And this is where it's going to be in the root of the volume. Okay, so normally in the C, so as soon as you open up Finder, it's in the root of the system drive and it's right there. Okay, but it is hidden, so you do need to look up, either turn on hidden files or do it from a terminal and do look for an LA file, right? Something that is archival on it. Now, this is a SQLite based framework, and normally it records every file system change on the system: creations, deletions, renames, external drive mounting. FS Events D is what you want to look for. Now, unlike standard file journaling, this file normally can get overwritten quickly. Reverse that. This file is persistent. File journaling can get overwritten quickly, right? Because it's normally a rollover file. It is only so large, and once it gets to a certain size, we normally roll over the file. But FS Events D is a persistent drive, and so that's why, as an investigator, this is it's a gold mine file for us, because we can use tools like FS Events Parser to prove that a user downloaded a specific intellectual property file, moved it to a SanDisk USB drive, and then deleted the original file, effectively proving data theft even if the USB drive is missing. Okay, so FS Events Parser is the tool that we would use for that. Now, unified logs, starting in Mac OS Sierra, remember, in 10.12, Apple replaced the standard plain text syslog files with unified logging systems. These are located in the VARDB diagnostics directory, as you can see on the screen, and are stored highly compressed. They're normally compressed, mainly because they're in a format called tracev3. You can't open these files in a text editor, but you can use the native log command to parse them. Because they generate millions of entries per day, filtering is mandatory. For the exam, you need to recognize the syntax. So if I showed you a syntax that log, show, predicate, process, sudo in the last hour, this command basically shows us anything that was privileged escalation attempts in the last hour. Okay, you should be able to just look at this and be able to read the command. Now, the exam will not require you to write this command, but it will require you to at least read it and decipher it. Finally, we're going to look at the user activity artifacts. Okay, Spotlight is the macOS search index. To enable instant searching, it stores all the metadata for all the files on the disk. Examiners can query this database, and it helps us find evidence of the connected volume, like names and historical file paths. Now, quarantine events, on the other hand, is tied to Apple's Gatekeeper antivirus. So Gatekeeper is like Defender in Windows. Okay, Gatekeeper is their antivirus technology that's built in. When a file is downloaded from the internet, it is tagged, and examining the SQLite database, okay, for the Spotlight database, for example, we can actually see the URL that it was downloaded from, the download's timestamp, which application like Safari or Chrome, who downloaded it, and whether or not it got quarantined, okay? Because sometimes you want to know if it's quarantined, and this is where the database is located. It's quite long. Libraries, preferences, com, Apple, launch services.quarantine events v2. That's a mouthful to go through that. Ooh, all right, so those are the artifacts that we would be looking for within Linux or Mac. At least a high-level version of it. Make sure that you read the chapters, get a little more in depth on these. But just remember, in Linux, the inode manages all metadata except for the file name. System logs are going to be in var log, and the bash history files are definitely going to be usable to see what history commands were ran. Now, in Mac OS, on the other hand, remember that we use APFS now, and it uses containers and volumes, with snapshots providing a safety net against data destruction. FS Events tracks historical file movement. Unified file logs are specifically unified logs require a log binary to read, because remember, there's millions of lines here, and so we need to be able to search them. And then the commonality between the platforms is we may need to understand that we need to understand basic CLI commands. So we need to be able to use grep and strings and dd, and as well as all of the navigational commands for both file systems. Just knowing that most of those commands are going to be the same because, well, guess what? Thank you, Mac, for being a glorified BSD system. But remember, there's still going to be tools on Macs that are going to be unique because it is still Mac. And then knowing also that Macs by default are as encrypted through their chips, so you can't just pull a hard drive and image a Mac. All right, so that completes the deep dive into Linux and Mac forensics. Remember, mastering those command line and specific file system structures will give you a massive advantage on the exam, and even in real-world enterprise incident response, whether or not you work in a forensics as a forensics investigator, incident response, or even just a security analyst. If you have any questions, let me know. Otherwise, I will see you for Chapter 8 when we deal with network forensics.